today's lesson, I will cover in terms of the basic concept of the convolutional neural networks. So basically, I will try to keep the explanation as simple as possible so that you can grab the idea behind what is the convolutional structures of the neural networks. So once you understand the basic concept of the platform, it will be quite easy for you to move on to the next step, which is learning the advanced model, understanding the model and how it works. So let's get started. So basically this is the topics that I will cover today. So the first one is the comparison between MNIST dataset using the artificial neural networks, which is the previous dense model that we have learned, and comparison with the convolutional neural networks. The second one, I will give some simple explanation about the architectures of the CNN. So later on, the next four parts is the basics or the foundation of the CNN, which is the first one is the concept for the edge detection and convolution. Second is the padding. Third is the stride, and finally the concept of pooling. So previously we have trained the MNIST dataset, which consists of the handwritten digits, which is around 60,000 samples, by using the standard artificial neural network multiplayer perceptron. So this is our previous model in which we have the input layer, the hidden layer, and then the output layer. So in our previous case, we have input with the 784 neurons, hidden layer with 524 neurons, and then the output layers that corresponding to the 0 to 9, which is consists of the 10 neuron. So for the training sessions, when we execute that things, the highest performance that we will get is 98% for the training, and validation is 97%. So this is after the optimal epoch that we take around 4 epoch. So now let's extend this model to learn for the MNIST dataset by using the convolutional neural network structure. So how we able to modify that thing? So if you can see from here, the green part is the extension of part that I have plugged in to this particular model in order to learn the MNIST dataset better. So the green part will consist of the 3 convolutional layers and 1 flattened layers. So the purple part is actually the same model of the artificial neural networks that we have modified in terms of the 2 parts. The first part is in terms of the inputs. So convolutional neural networks will receive the 2D inputs. So for this case, so we will just plug in the size dimension of 28 times 28. And then the next part for the hidden layers, previously we used 112, but now we reduce the numbers to 64. So this is the only modification that we made to the previous model in terms of the original structures. And apart from that, we add the convolutional layer. So the aim of the convolution layers is for extract features. So we define this thing as the thing that can learn the local feature extraction. So basically for the image processing, if you have an image, so you need to extract whatever important features such as the edge, the corner, then etc. So for the neural networks, you just need to plug in image, and then neural network will try to find what is the tangible features that can be used in order to learn the model much more better. So if we use this model to train our MNIST dataset, so basically this is the performance that we will get. So the training accuracy, we get around 99%, and the same with the validation accuracy. So this is one thing, by using just simple extension of the neural network models, we're able to obtain much higher accuracies for this training session. So let me show you a bit about the structure of this model. So if you still remember our previous model, we use this particular structure. So for this structure, okay, so for our previous model, we use this particular structure in which we have the dense model, and then we have the hidden layer with 112, and then we have the output layers with the 10 neurons. So this is our previous model. So for the convolutional neural networks, we will use almost the same structures of programming. Only for this model, we just modify a bit in terms of the structures. So the same thing. So first we add the convolutional layers, add another max pooling, convolution layers, max poolings, and then later on, finally we add the dense network, which is our original artificial neural networks. So if you can see from here, so from this particular graph, so the performance is at peaks, which is around the epoch number 3, and then at epoch number 10, the performance is much more higher than the rest of the epoch. So in this particular case, we select the highest performance for this particular model, and then we can say that this is the optimal solutions or the optimal parameters tuning that can be used in order to give the higher accuracy of the training and validation dataset. You can play around later on with this programming by changing the number of the, let's say, hidden layer in the dense unit, or you can also add, you can stack the additional convolution layer in order to learn much more features from the MNIST dataset. So this is regarding the models. So now let's learn about the basic model of the convolutional neural networks. What is actually happening behind the curtain for this model, and why the model is important, and what we can tune in order to improve performance of the convolutional neural networks model. So for the convolutional neural network architectures, so first thing first, we just feed straightway the input image to the models. So usually the input image will be in the 2 dimension, and with the n channels. N channels means that for the grayscale image you have 1 channel, but for the RGB image you will have 3 channels. So usually most of the times the input dimension will be consistent when you plug into the convolutional model. So you don't have to worry much about this thing, because of when you feed the image to the model, it will be done automatically by using the internal image processing toolbox inside the Python. Second thing, this is what you need to do before you plug in the image. So most of the image, let's say for the grayscale image, the pixel will be around 0 to 255. Before you plug into the convolutional models, you need to normalize the value to 0 to 1. So how you're able to do that thing is by using, just by simply divide all the input pixels value to 255, so that you're able to normalize that thing between 0 to 1. So the next part is that for our previous simple model, we just stack 3 convolutional layers. So in these convolutional layers, for the first layer, we have the convolutional filters and the max pooling. Second, we have another filters, which is 64 filters, and also the max poolings. And then for the final layers of the convolutional model, we have the 64 filters, in which the size of the filter will be 3 by 3. So we stack everything here. So the convolution layer will work on the 2D, because we fed the image in 2D, so it will process the things directly in the 2 dimension. So the aim of these 3 things is to enhance or extract the local features. So how the convolutional able to do that things? So first thing first, you need to remember that for every layers, let's say the layer 1, layer 2, layer 3 of the convolutionals, we have 32 filters. 32 filters means that we stack all these filters. In this case, we have 32. So for the second layer, convolutional 2, we have 64. And then for the final layer, we have also 64 filters. So the question is that what is the filters? So for the filters, usually we will use either the 3x3 or 5x5 dimension of the filters. So the filters is just a simple kernel functions which will be used in order to enhance or extract some important features from the image. So this is some example of the three different filters. So this is let's say I name it as the filter number 1. For filter number 1, it will be used in order to enhance the diagonal features from the image. In this case, around negative 45 degrees. So the second one, it will be used in order to determine or enhance the center point or in the inside of the image, since we find what is we find the X features from the image. And then finally, for the filter number 3, it also be used in order to enhance the diagonal in the 45 degrees features. So all these filters will be applied straightway to the input image in order to enhance the features, in order to extract the features from this particular image. So in this case, we just have 3, but in general, for this model, we have 32 type of filters that almost the same with this part. So for the every filters, you notice that we have some values, which is all the values will give the arrangement of the values will enhance different type of features that you want to extract. So in this case, we have the 32 filters. So all the filters value here is known as the weight to the neural networks for the convolutional model. So for this case, if we have 32 filters, means that we will have around 32 times 9 parameters. And then later on we have the bias, in which the bias will be the number of the filters. So I will explain the details later on. But for the time being, you just need to remember we have the filters, and then we stack the filters in the convolution layers in order to extract or in order to enhance the type of features that you want to enhance from the given image. Okay, so for these filters, let's say for the convolutional layer number 1, so you have these filters, it will be applied straightway to the image. So if we move on to the second convolutional layer, which is convolutional 2, so this type of filters will be applied to the previous stage of the convolutional image, which is known as the feature map of convolutional image number 1. So for the convolutional 1, the input will be the input image, the output will be feature maps that consist of 32 images. So for the convolutional number 2, the input image will be the feature maps from convolutional 1, and then the output will be the feature maps of the convolutional 2 with 64 images. So the same thing with the next convolutional layer. So once you have stacked the 2D part of the convolutional layers, so the next part is we flatten the layers. Flatten the layers means that in this convolutional tree, we have the 2D dimension of the image. So we need to flatten that thing in 1D in order to plug in that to the dense model. So the dense model is almost the same with our previous artificial neural network structure. So this is in general the overall simplest architecture of the convolutional neural networks that you can use in order to improve accuracies during training and validation of your dataset. So let's just learn a bit about the programmings, in which how we're able to modify or how we're able to plug in the design of this model to our programmings in Python. So for this case, the first part, we just add the convolutional layers with, in this case, we have 32 filters. and then with 3 by 3 filters. Remember, you can change this thing. Either you want to put 64, either you want to put 16, or whatever you want to use, as long as you have the optimal designs. And then the second parameters is the 3 by 3. So as I mentioned, we have only two type of dimension of the filters, either 3 by 3 or 5 by 5. But most of the times, most of the researchers we use the 3 by 3 filters. So the next part we have the activation. Activation is the simple activation function that will be outputting the output depending on what you wish to have. So this is the final part is the input shape. So that's the reason that I mentioned you don't have to worry much about the dimension of the image that you will plug in. So everything will be rescaled to the one that you have defined here. So this is the first part of the programming. So for the second part, which is the yellow part, so this is the stack of the convolutional filters until the flatten. So how we able to do this thing? Let's say for the convolutional two parts, you just need to add layers dot convol 2D, and then we have 64 filters with 3 by 3 dimension. Activation will be the ReLU. So the next part we add the poolings, max pooling. Previously we also have the max pooling. So just add the max pooling with this is the dimension. So in this case we have 2 by 2. So usually for the max pooling we will use the dimension, the same dimension 2 by 2. You can put a 3 by 3, but this is the simplest, the common one will be based on the 2 by 2 max pooling. So the same thing for the final layer. For the conventional 3 layers, you just need to add the layers. In this case, we have the same thing, 64 filters with the 3 by 3 dimension. Activation function will be the ReLU. So we don't have any max pooling for the last convolution layers. And then later on, just flatten that thing from 2D to 1D representation. So finally, this is the dense model. It's quite simple. You just need to add the model. So in this case we have 64 hidden neuron, and then finally the output will be 10. So this is almost the same with the previous artificial neural networks model, in which you just need to add the activation function, then the number of neuron that you wish to add for the dense layer. So for the structure of the programming is almost the same I have mentioned. So you just need to add this model. You can modify later on, you can change the parameters, it's up to you, and then you can look at what is the effect when you change every parameters. So the next part I will cover here what is the edge detection, which is one of the important features that can be used in order to enhance the features from the image I've mentioned. Whether you want to enhance what the diagonal, the center of image, the corner, and etc. So there is the part in which that thing will be happening, which is the combination of the edge detection and the convolution. So first is what is the edge detections. So the aim of the edge detection is to highlight the transition location of image density looking from the small window patch. So what is the statement means that let's say you have this image. So small window patch means that you have some kernel, just small kernel dimension, let's say 3 by 3, 5 by 5, and etc. And then what we will do, so the kernel will be slided throughout the image, and then later on we will find the transition location. Means that let's say for this location, so usually for this location we will have the, let's say for this location we have some the transition point here, so it will be highlighted in our edge detectors. So once we apply the edge detection, so this is type of the features that will be extracted, and then we'll pass this thing from layer to layer in order to depending on what type of features that you want to enhance. So there are many examples of the kernel filters. This is just some example that I can found from the internet. So for every kernels, it will have some individual function. Let's say for this first kernel, it will be used in order to detect this line, which is in this case is the horizontal line. So this is the vertical line, diagonal 45 degree, diagonal negative 45. So the same thing, this is the the same filter, diagonal, uh, and this will be also the same thing but with some weight. So depending on the arrangement, you can extract many type of features from the image. So in the convolution neural networks, so the value will be determined automatically when you perform the training process. So this is in which you have the way of training will be plugged in here. So let's say if you want to improve just the diagonal part, so when you're training, you improve the diagonal part. So most of the part will be zero. Only the part that you wish to highlight will have some values that will be increment from time to time as you perform the training process. So the second part is we perform the edge detection by using the process named as the convolutional process. So for the convolutional is basically two type of process. The first one is it will be multiply the kernel with the image, means that for every point in the kernel will be multiplied with the image, and then later on just sum up all the results of the multiplication. So this is some simple example how we perform the convolutional process. So first thing first is that if we have this type of image, and then we have this type of kernel. So this kernel will be used in order to determine the horizontal lines in the image. So once we plug in the kernels here, so multiply means that you just need to multiply every part here. So in this case, 63 times -1. This part also the same, 63 times -1. This is 190 times -1. So this part for the second row, everything will be 0, and then the third part 63 plus 255 plus 255. So you just need to multiply every part with its corresponding kernel value. So just multiply everything and then sum up everything. So for the first part, so we have the value of 257, which the result of the convolutional process. So the next stage, we just move the kernel to the next part and then perform the same process, means multiply everything and then sum up everything. So the second part we have 322, and then the same thing with the rest. So we repeat all the process, and then eventually we have a series of the outcome of the convolution layer that we define as the feature maps in the convolutional model. So one thing that regarding the convolutional process, once you perform the convolutional process, if you notice that your output image dimension will be slightly reduced. So the output dimension slightly reduced because of, if you think that for this type of kernel, the value allocation that we can perform the convolution process is starting from this part, because of it will cover the whole areas of the image. You cannot perform the convolution process here because you don't have anything in here. So this is the location where the convolution process will be valid, so and end up in here instead of the final part here. So it will end up here. So there is one thing, one of the reason that when you perform the convolution process, your output image dimension will be slightly reduced. So this is the simple equation. It will be reduced according to this equation, in which for this part, ID is your input image dimension. So in this case is 1, 2, 3, 4, 5, 6, 7, 8, 8 times 4. And then KD is the dimension of your kernel. In this case is 3 by 3. And you need to plus with 1. So for this example, our dimension of the output in terms of is width The original one is 8, so minus with 3 dimension of the kernel plus 1, so your output will be 6 in terms of the width. And then in terms of the height, you have input, it will be 4 minus the kernel 3 plus 1, so your output dimension of the height will be 2. So this is the same thing with the output that we found here. Means that we have 1 2 3 4 5 6 6 times 2 in terms of the output of the image. So you just need to remember this thing. So when you want to find what is the dimension of the output as a result of the convolutional process, you just need to know the dimension of your input image minus what type of kernel, 3 by 3 or 5 by 5, and then plus 1. So then you're able to determine the output dimension of the convolutional process. So this is an example of the convolutional process in which you have the input image. You have series of the kernels here, and then this is the result. So if you can see from here, so this type of kernel, we want to enhance in terms of the horizontal line. So in this case, you see most of the part will be 0. Only this part, which is the transition point, we have some value here. For every convolutional process, let's say this is type of the filters. So all these filters will be responsible in order to highlight some small patch or small features in the image. So if you have, let's say, 3 filters, so these 3 filters will be used in order to enhance the features for this particular region, and then another filters will enhance another regions. So all the things will be concatenated together in the final dense layer in order to be utilized for the learning the models, and also will be used to validate the learning pattern. So we have learned in terms of the convolution in the 1D image, which is you have the grayscale image, and then you apply the simple convolution kernels, you apply the kernels and then perform the convolution process for the 1D image. So how about if we have the high channel image? It means let's say you have this image with the 3 channels. So for instance, the RGB image means that you have the red channel, green channel, and blue channel. So in this case, we have the 3 channel. So how we are able to perform the convolutional process? So first thing first, you need to remember, if you have the high channel image, so your kernel will also need to have the same channel dimension. Let's say you have the 3 channel here, so your kernel will have the same channels. In this case 3, you have 3. If you have, let's say, 32 channels, so the same thing with your kernels will have 32 channels. So for the kernel, the same thing, you have 3 channels. Kernel will have also 3 channels that you stack together. So in this case, the kernel will have 27 features. So how we perform the convolutional process? We just the same thing with the 2D image. Instead, for this case, we just apply that things in terms of the volume. So last time we just multiply the blue part here. But for this case, you need to multiply all the 27 location instead of the just 9 location. So let's say for the first part, this thing will be multiplied with the first part of the image, and then second part with the second part of the image, and then final part with the final part of the image. So you will have around, let's say, I just put this is convolutional 1 plus convolution 2 plus convolutional 3, and then until the convolutional 27. You just need to sum up everything. So this is the output of the convolutional process. So the same thing, the cube will be slided through the image, and then for every process you just have a simple single picture image, because of you slide the cube through the image, and eventually you have this C27 value. The total of this thing will be plugged in this part. Okay. So now, what if we have two layers? We have another channel of the image. So this is your first kernel. We have two kernels. Sorry, if you have two kernels, this thing. So how we able to do that thing? So we just repeat the same process in which you perform the convolution in the second image. Sorry, you have the image. You perform the convolution with the other type of kernel. Then for this kernel, you will have the result. So the result will be stacked together. So this is in which you will have the feature map of this type, which is 36 times 26 times 2. If you just apply just single kernel, so you have just a single feature map. If you add more kernels, let's say you have 32 kernels, so you will repeat the same process in the image by using different type of the kernels, and then later on the result will be stacked together in the output feature map, and then you can increase the channel of your output in the feature map. So this is the process of how you're able to apply the convolutional process over a high dimension image. So you need to remember, let's say for our previous model, we just have one channel of the image, 28 times 28 times 1. You move to the first convolutional layer, conv1, you have 32 filters with 3 by 3. So in this case, first you just apply the single channel. So this is the same process. So but the second part, for the convolutional 2, you have 64 filters with 3 by 3. So in this case, your kernel, for the 64 kernel, let's say the first kernel, the channel must be same with this thing, which is 32 channel. So you apply that thing. So you have 64 types of this kernel in this side. So the process will be repeated for the next convolutional layer. So the next part that you will learn is about the padding. So padding is the concept in which you add border, or we call this thing as the border extension. So if you still remember from your previous convolutional process, if you apply every kernel to the input image, your dimension will be slightly reduced in a factor of input minus kernel plus 1. So if without the padding, so if you apply this type of kernel, so eventually you will reduce the output dimension of the image. So padding means that you will actually add border extension. So in this case, if we have the padding of 2, so this is the original image. So we add some padding here with a factor of 2, means that 1, 2. So now if we perform the convolutional process, your output dimension will be the same as input dimension. So you don't have any reduction of dimension when you perform the convolutional process. So previously for the without padding, so your output dimension equation will be input minus kernel dimension plus 1, which is in this case, if your input is 5, so your kernel is 3, input is 5, your kernel is 3, plus 1, so your output dimension will be 3 by 3. So with the paddings, so we add some extra information, which is the padding information in the equation. So our equation now becomes input minus kernel plus 2 padding plus 1. So for this case, let's say you add the first padding, you just add the padding here. So you add the padding here. For this case, you have the input of 5 minus kernel plus padding here. So padding will be a factor of 2 for every extension that you will make. So you add the padding. So in this case, your input image is 5, your output image will also 5. So the concept is quite simple, means that for every input image, you just pad that thing with how many border extension that you want to have with a factor of 2. So let's say if you have 2, if you have 4, and etc. So this is the way that you will calculate the output of your padding. In general, in a simple way, padding will be ensure that your output dimension will be the same with your input dimension when you perform the convolutional process. So this is some example of the convolution process when you apply when you implement the padding. So it means that your output will be same with the input dimension. Okay. So let's move on to the next part of the concept, which is the stride. So stride in a simple way, something like the skip convolutional steps. So previously, for the every convolutional process, what you will do is that you will actually implement that thing throughout the image. So stride means that you just skip in some part of the process. So the aim of the stride is same with the padding, but it will be used in order to downsample image in a different way. You downsample image, but with a different type of factors. So example, if we have the convolution process with the stride of 2. Stride of 2 means that every convolution process we have stride of 1. So it means that you just add move from one step to another step. So this is what I mean by stride by 1, means that you start in this location, you move to the next part, and then you move to the next part, and then you move to the other part. So this is stride by 1. Stride by 2 means that if you start with this location, stride by 2 means that you just move on to the next part here, means you skip this part. So this is the mean of the stride by 2. So let's say for this case, if I perform the convolution process by using the 3x3 kernel for this first location, so if you put stride by 2 means that you will only implement your kernel in the first location, second location, third location, and fourth location, and then you have the output image. So for it will be, if you look at this illustration, so it means that for this input image you have 1 2 3 4 5 times 5. So once you perform the convolution with stride of 2, your output dimension will be only 4, because of you have only 4 valid location that you can perform the convolutional process. So for every stride that you add to the system, so it will reduce the dimension of the image by using this factor. So it means that for this case, you have the input dimension minus the kernel dimension over what is the stride that you want to put. Let's say if you want to put 2, then it will be over 2 plus 1. So for this case, you have the 5 by 5 image with the 3 by 3 kernels. Then you have stride of 2. So your output image will be 2 by 2. So in this case, if you perform stride, so this is your output dimension from your input 5 by 5. So it's quite easy to understand in terms of the stride process. So the next part, which is the final part, is the pooling concept. Pooling is one of the simple ideas that will be used in order to reduce the dimension. So the same thing. So the aim of pooling is the same with the stride, which is to reduce dimension in almost the same way, which is it will be reduce the thing in half dimension. So the pooling process, you just extract the windows from the input features and then outputting the max value of each channel. So what is the meaning of this statement? So but first thing is that usually the pooling will be implemented in 2 by 2 windows with a stride of 2. Means that we jump the process to skip some of the location and then perform the pooling layer. So let's say this is some example on how we perform the pooling process. So let's say for this case, if we have 2 by 2 pooling layer, so for the first location here, so the maximum will be 8. You just need to plug in here 8, and then stride means that you just skip one step and then move on to the next part. So for the second part, you have the maximum dimension, maximum output will be 6. So you just put the maximum output here, and the same thing is 9, and then finally is 9. So this is the output as a result of you perform the pooling process in the input image. So basically for the dimension reduction, so the equation will be something like this for the pooling process. It's almost the same with the previous equation. Only in this case is we just make the equation specific for the pooling process. So you have the input image minus the KD is the dimension of your pooling kernel. So in this case is 2 by 2 over the stride. So stride will always be 2 for every process of the pooling layer. So for this particular case, you have the input dimension of 4 minus the kernel of your pooling, which is 2 by 2, over stride, which is 2, usually 2 plus 1. So for this case, if you have input image of the 4 by 4, so your output image will be 2 by 2 after you perform the pooling process. So now you have learned most of the basic concept of the convolutional process from the structures, the every part of the models, and then how we're able to calculate the output as a result of the process. So now let's summarize some sort of the equation for every process. So the first one is for every dimension of the convolutional process, you can calculate the output dimension by using this simple equation in which ID is the input image or the input features dimension minus the KD is the kernel dimension 3 by 3 or 5 by 5, and then padding, how many padding that you want to use, 1 or 2, and then later on stride means that how much step that you want to skip during the convolutional process. So basically this is the equation in which the input minus kernel plus 2 padding over stride plus 1. So the next part specific of the max pooling output. So for this output you can do the same process in which for this case we have the input image dimension or the feature map dimension minus this thing is the kernel dimension of your poolings, usually 2 by 2, over the stride. So for the max pooling process, your stride will always be 2 and then plus 1. So the final equation that I want to highlight is in terms of the total trainable parameters. So for every layers that you plug into the convolution process, so you need to calculate the weight. So all the weights will be defined as the parameters for the structures. So in some of the design, you need to ensure that your parameters will be quite acceptable or optimal in order to ensure that it will be adapt to the particular model without sacrificing the performance of the system or without the overfitting process. So that's one of the reason that is quite also important to know how many parameters can be used in order to train the models, and too many parameters means that there is some tendency of the model to overfit and etc. So now let's use this particular equation, every equation, and then implement it in our simplest model that we have that I have explained previously. So just recap this model in a simple way. We have the input image with the 28 times 28 dimension. We have the first convolutional filters with 32 filters, 3 by 3 dimension. Second convolutional model, you have the 64 filters with the 3 by 3 dimension. First filter you have the max pooling, second filter also you have the max pooling, And then for the third filters, which is the final layer, convolutional 3 layers, you have the 64 filters with a 3 by 3 dimension, flattened, and then we have one hidden layers and then one output layers. So first, let's calculate the dimension of every process. So for the first part of the calculation, so the output of this part here, if you wish to calculate the output dimension, so your input will be 28 times 28. Okay, so means that you have the input, you just recap this equation: input minus kernel plus 2 padding over stride. So in this case we don't have any padding, so padding will be equal to 0, and then stride, because we don't skip anything, so stride will be equal to 1. So you are left with input minus kernel plus 1. So we just utilize that equation. So for the first convolutional layer, after we perform the convolution, the output dimension will be, input is 28 minus your kernel will be 3 by 3 minus 3 plus 1. So after you perform the convolutional process for the first layer, your output dimension will be 26 times 26. Now next part is you implement the pooling with 2 by 2 filters. So your input of the pooling will be 26 minus the kernel dimension of your max pooling is 2. So since stride, for every max pooling, stride will be 2, so over 2 plus 1, so your output will be 13. So means that for this case, output for the first part of the convolutional layer will be 13 times 13 times 32. 32 comes from the number of filters that you put in the first convolutional layer. So now next we move on to the second convolution layers. So second convolution layers, you have the 64 filters with 3 by 3 dimension. So input for this thing is the output dimension of this part. So the output dimension for the convolutional one is 13 times 13 times 32. So it will be the input for the convolutional 2. So first let's calculate the output dimension. So for the first part, which is the convolutional process, your input will be 13 minus your kernel dimension will be 3 plus 1. So your output of the convolutional process will be 11. So the next part, you apply the max pooling. Max pooling means that your input of the max pooling will be 11. So your max pooling dimension will be 2. 11 minus 2. So over 2 plus 1. So you have the output of 5.5. But for this part, you just need to consider the integer part of that thing without the floating point. So we have the output dimension will be 5 times 5. So 5 times 5. So you will have the kernel. Since you have the 64 kernels for the second convolution layer, so your output dimension of the convolutional 2 will be 5 times 5 times 64. So we move on to the next part, which is the convolutional 3 layers. So for the convolutional 3 layers, it will receive input from the convolutional 2 layers, which is the input dimension will be 5 times 5 times 64. So if you apply the first part of the convolutional process, so it means that for this thing, your input will be 5 minus your filter will be 3 plus 1. So the output dimension of the convolutional process will be 3. So if we stack the thing together, so your output of the convolutional 3 process will be 3 by 3, 3 times 64. So this is the whole dimension after you implement the convolution 3 layer. Since we don't have any max pooling in the convolutional 3, so means that for this case, the output will be maintained to the convolutional process. So the next part, we perform the flatten. Flattens means that we just multiply everything here. 3 by 3 by 64, you have 576 model. Sorry, the dimension will be 576. We just set that thing in here. Means that You just stack this thing in here until 576. So the next part for the hidden layer with the hidden neuron, so the upper dimension will be 64, the same thing with your neuron, and then the same thing with the output here. So this is basically the process on how you're able to calculate the dimension, output dimension for the every convolutional layers. You can try to look at the model, let's say from the LXNet model, VG model. So for every part of the model, you can try to look at the dimension of that thing. So it must be consistent with this particular equation. And then for once you know this thing, you can easily determine the expected output dimension for every layer that you perform the convolution process. So this is quite simple because we don't have any stride and padding, but you need to remember we can put the stride and padding in every convolution layer. So you just need to plug in that thing into the formula to know that what is the expected output dimension. So the second part is to calculate the trainable parameters. So for the trainable parameters, so the equation will be total weights plus total bias. So for every layer, we have the weights, which is I have mentioned that the weights will be the kernel, the output in kernel. So means that in the filter, you have the kernel, let's say 1, 1, -1. So that is the weights. So we determine the total weights by using this equation, means that this is the kernel dimension. This is supposed to be multiplied with channels and then multiplied with kernels. And then for every layer, if you still remember, usually we have the bias. Bias will be used in order to make sure that your output will be much more easy to converge. And then the total parameters for every the convolution model will be total weights plus the total bias. So let's implement this equation in this mathematical model. So for the first part of the convolutional layer, so I just clear the screen first. So for the first part of the convolutional layers, so if you want to calculate the output parameters for this thing, so for the first layer we have the 32 filters. We have the 3x3 filters. 3x3 filters multiplied with the dimension of your input image. In this case, we have dimension of 1. And then how many filters that you have here is 32. And then plus the bias. So in this, bias will be the same with your number of filters. If you have 32 filters, then you have bias. So for the first part of the convolution process, you have the you have 320 parameters, trainable parameters. So move on to the second part of the convolutional process. So for the second convolution process, you have same thing. You have 3x3 filters, and then your input channels in this case is 32 times 32, and then you have 64 filters in a convolution layer 2, and then plus the bias in the convolution layer 2. So you have you have around 18,496 parameters for the convolutional layer number 2. And then for the convolution layer number 3, you have the 3x3 filters, the same thing, 3x3 filters, and then the channel of the input is 64. You have 64 here, and then you have 64 filters in convolutional layer 3, 64 filters, plus the bias in each of the filters, which is you have another 64 parameters. So you sum up everything, you will have around 36,928 parameters for the convolutional tree. So the next part, you flatten that thing, and then for the first hidden layer, so the trainable parameters will be the dimension of your output. So in this case, it is 576 times the number of your hidden neuron. So you have the 576 input times the number of the hidden neuron, and then of course you have the bias for this neuron. So in this case, you have the same thing, the same amount of the parameters for the hidden layer. And then finally for the output layers, you have the 64 neurons here and then 10 neurons here plus the bias. So you just need to add this thing, 64 times 10 plus the 10 bias, finally you have 650 parameters. So all the parameters will be summed up together in order to get what is the total parameters that will be used for this model. So let's compare the outcome of our equation, our calculation with respect to the summary of this model. You can easily determine this thing by using the model.summary command. So for the first layer, so the total part, okay, let's look at the dimension. So the first layer, the dimension will be 26 times 26 times 32. So this is the first, which is after you perform the convolutional, you have the 26 dimension, okay, with the same channel. So for the max pooling, you have the 13. So you have the 13 here. So I just plug in everything, 13 times 13 times 32. So this is the first convolution layer. Move on to the second layer. We have for the max pooling, for the convolutional, 11 dimension will be 11 times 11, of course, times 64, because of this is the dimension of the number of filters. After the max pooling, output dimension will be 5 times 5 times 64, which is 5 times 5 times 64. So finally, in the output layer, in the final convolutional layers, your output of the convolutional will be 3 times 3 times 64, which is 3 times 3 times 64. So for the flatten, 576, okay, and then the dimension, this is 64, 10 will be the same. So now this is in terms of the dimension. So the next part is the total parameters. So the first convolution layer, total parameters will be 320. Second layer will be the same, 18,496. The third layer is 36,928. And then the hidden neuron, which is the same, 36,928. And then finally for the output layer will be 615. So that's some simple explanation of how you're able to implement the convolutional models, the basic structures. So the next part we will cover up maybe in terms of the more advanced model of this thing, or you can explore that thing more easily once you have the basic idea of the convolutional neural network models. So that's all. Thank you very much.